Hey guys, so I'm currently studying for my physics midterm, and I'm going over chapter 24, 25, and 26 chapter problems, and these are chapter 24. Um, first it's asking us to, first we have to see what we're looking at, right? We're looking at a, a circuit with 9 capacitors in total, with the C1 and C2. Given their values, so first we're gonna go ahead and just do A. So compute the equivalent capacitance of the entire network of 9 capacitors. For this one, I'm gonna work on green. I'm gonna work with green. Sorry. So we're actually essentially just working backwards. Where C1, C1, C. So these are in a series, so we can find the C equivalents for that. We're gonna label this CEQ1. Okay. CQ1 is equals, so let's just work this out. It's going to be 1 over 6.9, and there's 3 of them, so this essentially just times 3 to the negative 1, because it's the inverse. So it's 1 over CEQ1 is equals 1 over 6.9 plus 1 over 6.9 plus 1 over 6.9. It's essentially the same thing. When we do this calculation, we should end up with 2.3 microfarads. And then this series is in a parallel with this capacitor right over here. With this capacitor. So we're just going to label this new C equivalence 2. And since it's in the parallel, and capacitors in the parallel, you just add the capacitance together. It's going to be 2.3 microfarads plus C2, which is equals 4.6 plus 2.3 is just 6.9 microfarads. And from here, we can actually conclude, or we can see that that's with every series of 3 C1 capacitors, it's going to be an equal of C2 would equal to C1, if that makes sense, right? So we could do the same thing here again. Okay, so we're just gonna label this CEQ3, and I'm looking at this now, and then since it's very similar, not even very similar, it's quite exactly CEQ1, we can just say the CEQ2 or CEQ3 is equal to CEQ1, where it's going to equal 2.3 microfarads, and then so on and so forth. We can put this in the parallel, put it in the parallel with the C2, label the CEQ4, and essentially this is the same thing as 2.3 microfarads plus C2, which is 6.9 microfarads. Finally, we're going to go ahead and just find the series in these 3 capacitors, C1, C2, and then another C1. But C2 is equal to 6.9 microfarads. So we conclude that CEQ5, or we'll just say the CEQ total, is equals 2.3 microfarads. So that's how we would solve. This is how we would solve the first one. So we're gonna go ahead and just rewrite this real quick. So 1 CEQ total equals 2.3 microfarads from the 9 capacitors in our circuits. Very simple. So now for second one, it says compute the amount of charge on each of the three capacitors near the battery, assuming the battery's voltage is 420 volts. So for this one, so this is the system that it wants us to look at, where it's C1, C2, and another C1. And then the voltage is equal to 420 volts. But this voltage is split within three capacitors. So we can just say that the voltage is split between three capacitors. Since they all have the same charge, it's in a series. And in a series, the charge is all the same. So we'll say that 420 volts is split into three. So we can say that 420 volts divided by 3. So this is the voltage running through each capacitors in this series. And then if we do this, it should give us, I believe it's just 140 volts. So we can go ahead and just rewrite this real quick. So our V is equal to 140 volts. So now we can recognize that the voltage in the capacitor equals Q over C. So if we rearrange this to solve for Q, which is the charge, Q is equal to V times C. So this is essentially just what we're doing. So for C1 and C2, they share the same capacitor values, so they will have the same charge. So we'll say that for C1, we'll label this Q1 is equal to V. V is just going to be 140 volts, and we're going to be using times C1. And then we can say that for Q2, this is going to be for the second capacitor, or C2, is the same voltage multiplied by its value. So we can solve. So Q1 is equal to 140 volts multiplied by 6.9 microfarads. So Q1 is equal to 966 microfarads. And if we solve for Q2 the same way, Q2 would be 140 multiplied by 4.6 microfarads is giving us 644 microfarads. So we're going to go ahead and just say for 2, C1 gives us C1 gives us 966 sorry, not even microfarads. Sorry, these should be in coulombs. I am so sorry. This should be coulombs. Microcoulombs, actually. Microcoulombs. So C1 has 9.66 microcoulombs. C2 gives 644 microcoulombs as well. Cool. So we can go ahead and just move on to number 3. So for number 3, again, assuming a battery voltage of 420 volts. So we can just rewrite the same thing. V battery equals 420 volts. What is the voltage drop from point A to point B? Okay, so from point A to point B, So we can just recognize that we're looking at. So let's actually kind of redraw. So we have A, we have B, and then we have C1, C2, C2, C1. And it's asking us to find the voltage drop from A to B. So we have V is equal to QC. So VAB, it's going to be the charge. So it's the charge on this. So since VAB is equal to QC, the voltage VAB is just one third of V. And then from earlier, we said that V is equal to 420 over 3. Okay. So then we can eventually just do VAB equals Q over C, where Q is equal to Q over 3 so then this gives us VAB is equal to Q over 3C. But since we're already given this, we know that Q over C is equal to 420 over 3 volts. So we can say that the voltage drop VAB from A to B is equal to 1/3 multiplied by 140 volts. And then 140 divided by 3 is 46.67 volts. So for number 3, we can just say that our V drop from point A to point B is 46.67 volts. Thank you.